Could someone please remind me what slide we were on from yesterday? Or last week? It was last week. I think we were on this one. We could have been on this one. I think it might have been this one. I'm not sure. If you wouldn't mind. Also, that's my kettle. I'll be right back. Yup. Thank you for the like, whoever just liked the video. Boy, the attendance is pretty low today, I have to say. I'm not sure why that would be the case. Maybe it's getting toward the end of the semester and everybody's like, well, I can just watch it anyways. Watch it afterwards anyways. Pardon me. So yeah, alright, I guess I'll just go from the slide I assumed we stopped on then. So let's talk data structures. Last time we were talking about linked lists. We were talking about graphs in general. Graph theory, graphs being collections of vertices and edges, directed graphs being graphs that have arrows instead of just edges. Generally speaking, pretty much all of the data structures that we will be dealing with will be directed data structures, because in programming code, the analogy for a directed edge in a graph is a pointer to another node. So, you know, directed graphs are, in some sense, less bothersome to implement than basically, if you have a bidirectional relationship, then that's more or less your analogy in code to an edge rather than a directed edge. I got a message, but where is it? Where is the message? Am I in the wrong team? I might be in the wrong team. Yeah, I'm in the wrong team. Jeez, man. Ugh. Yeah, okay. I was in the wrong team. Like a dummy. This is a fine window for chatting. All right. So, we were also discussing singly linked lists. A singly linked list is a graph where each node points to another node, or to one other node or no nodes, and no node is pointed to more than once. So it's a linear data structure. The way that you would implement this, using the records that the record type that we had discussed and implemented way back when we were talking about structs, the way that you would implement a linked list in a structure is you would include one self-referential pointer, which points to the next element in the list. This is good. This is cool. If we wish to refer to a singly linked list in main or one of our functions, we need only a single node from which we can access the rest. Generally speaking, when you have a data structure like this, going through the nodes by following the pointers through the data structure is called traversing the data structure. Anatomy midterm in 2 hours might explain the difference. How many people in this class are in the biomed? Because, like, 20? Well, 10. Well, still, I would have assumed that there were, like, 2 people in, like, biomed and mechatronics. That is interesting to me, that so many people would be, so many people would also be in the biomed stream. But yeah, that would explain the attendance for sure. Anywho, so each node points to the next node, and the last node points to null. We can, of course, test to see if a pointer points to null, so we can always tell if a node is the last node by the state of its pointer. Cool. 10 and 20, jeez. Huh. A lot of people want to build MRIs. Huh. Yes. That's interesting. Well, good luck to them on their anatomy midterm. Just remember, carpals, metacarpals, tarsals, metatarsals, and you'll be fine. If anybody who's watching this sees is actually anyway. So, if we wish to visualize, oh my god. Car alarms, jeez. If we wish to visualize what the linked list data structure looks like with the record data types in place, you get something that looks like this, where each one of these is a, this is like, each one of these boxes is one of the fields of the structure, and the next pointer is pointing to the next record object, and you just point, they self-point all the way down until you get one that points to null. The more information that is contained in the structure, the more advantageous it is to organize it in this manner. If you wish to, so the question is, like, okay, I'm getting ahead of the slides. If you want to pass the first node by reference to a function, keep in mind that within the function, you will have to dereference the argument to get to the first node's data. This is what the arrow operator is for. It is dereferencing plus field access. So what's the point of all of this? Why would you use a linked list versus an array? It seems like a lot of work just to get something that functions roughly like an array anyway. Well, because the list is not stored in contiguous memory, it can be dynamically grown or shrunk without having to copy the whole array. Because the next node is indicated with pointers, and those pointers may be modified, we can insert an element without having to move any of the other elements in memory. Of course, this is not the case with an array. If you wish to insert or delete an element in an array, you have to move the whole rest of the array over one way or the other to accommodate either the space that needs to be made or the space that needs to be consumed by either the insert or delete operation respectively. However, there are some drawbacks to storing things in linked lists. Because the nodes are not stored in contiguous memory, we can't perform pointer arithmetic to find a particular index. This means we need to follow the node pointers instead. We need to traverse the data structure in order to access elements of the data structure. For an array, accessing an element at a particular index is a constant time operation, i.e., it does not require the amount of time that it takes to access a particular element at a particular index in an array is not dependent on the size of the array because it's achieved via pointer arithmetic. However, with a linked list, the amount of time it takes to access an element at a particular index in the linked list is dependent on the, well, it is exactly the size of the index that you're trying, it's the value of the index that you're trying to reach, because you have to traverse the array to find that index. You have to travel through the data structure until you find the index that you're looking for, so that takes more time. Finding a record at index I takes I operations, whereas an array can do it in one. So, yeah, basically. So, one of the other drawbacks of a linked list, a singly linked list, is that it's only traversable in one direction. You can only go from the front to the back. However, if you wish to be able to move back and forth through a linked list, you may wish to consider the implementation of a doubly linked list. The doubly linked list is a singly linked list with an added condition that each node has an edge that points to the node that points to it. So, no new node may be pointed to more than once, and we're still essentially dealing with a linear data structure, but we have added an additional pointer to our structure. We now have a next and a previous. With the addition of one more pointer, previous, we have made a singly linked list node into a doubly linked list node. The first element's previous pointer will point to null, and the last element's next pointer will also point to null. When a doubly linked list increases the amount of while a doubly linked list increases the amount of bookkeeping, it also the whole point is that it makes the list traversable in either direction. So, obviously, if you have two pointers to deal with, if you think about something like an insertion operation, you're not having to reassign just one next node and then make the inserted node's next node into the previous the next pointer of the element before it. You have to do you have to perform the reverse operation as well with the previous the prev pointers as well as the next pointers. You have to connect both of them up. It takes twice as much time to do that because it's twice as many pointers. But generally speaking, the general way of it is that the amount of bookkeeping that you have to do to maintain these types of data structures is usually well worth it for the advantages that these data structures offer. So, there you go. So, if we wish to take a look at what a linked list looks like in terms of record structures, this is what you would be looking at. So, we've got a pointer to the linked list in this case. We've got 5 different records, which are all stored in disjoint areas of memory. Next points to the structure, next points to the structure, to the next, and then next terminally points to null, and then the previous pointers point backwards, and also the previous pointer of the first one points to null. Cool. So that's linked lists. If you have any questions about linked lists, I will hear them now, and please, if you have any questions, please speak up. Otherwise, we'll move on to our final topic for this, our final section for this topic, which is trees. Go to page 36. Pardon me. Where is the second pointer in that example? Here. So next is the first pointer in the structure. So structure, next. Previous, that's the second. Right there. So you'll notice that each structure, regardless as to whether the pointer points to null or points to another struct. Oop, I need to shush myself. They're all included. The space has been designated for them. Conceptually, they make sense. I just hope the code implementation isn't too tricky. Yeah, it depends on which operation you wish to perform, right? So I'll give you a hint about this. Generally speaking, these types of data structures lend themselves very well to recursive functions. So consider it this way. Let's take, for example, the indexing operation. Let's say you have a singly linked list, and you want to find you want to return a pointer to a particular element in the linked list, element I, right? So if you write an indexing function that starts with the first element in the list, you would say index. I should just type this. So you would write a function that looked something like, let's say, struct, let's call it rec. So it returns a record, a pointer to a record, index, and then we take a struct record pointer, and we take a record pointer, we'll call it current, and it takes an int index, right? It would be like if you think about it conceptually, if you perform the same operation on the next node but subtract the index by 1, then you have formulated it as a recursive data structure. So, like, this is a case where recursion makes a lot of sense. Again, you can always do this with loops, but watch how simple this is. So, we want to, if index is equal to 0, return current. If index is not equal to 0, we're going to assume that it's positive. Actually, we can do unsigned int. There we go. That way it can't be negative. We return index of current next index minus 1. So in this one operation, we are following current. So this is a point. Current is a pointer to this structure type. The arrow operation dereferences the pointer and gets the field in one operation. It's the same thing as doing current star current dot next with like this. So next is a pointer to the next structure. If we subtract 1 from the index, like, that's the same thing, right? But that is all that you need in order to, that's a complete solution to the problem. If you wanted to do the same thing with a loop rather than with a with recursion, you would have to do something like while index is greater than 0, I minus minus current is equal to current next. That might actually make more sense to you, but, you know, either way is valid. Whichever one you can get to work is good. But you can do these things, like, conceptually speaking, it makes like, these types of data structures are highly amenable to recursive solutions. But you have to be able to think recursively. That's the problem. So would we physical type the pointer equal null, or would we just leave them blank and it will automatically be null? No. So when you declare a pointer, it'll be filled with garbage data initially. So in order for this to be null, it has to be assigned to be null. You know, if you had a add node method, which if you add a node to the end, then it has to, you know, it has to have null. It has to be assigned null manually. Yeah. So, good. So, yeah. Good. I think that's everything to do with lists. Incidentally, I may have mentioned this last time, but programming languages such as Haskell and Lisp, Lisp stands for List Processor, use linked lists as their default data type for where C uses arrays. Something like Lisp or Haskell uses these guys natively as their default aggregate data structure. So, let's talk about trees. It is a Christmas tree with a heap of presents underneath. We are not inviting you home next year. This is funny. Because we're going to talk about trees! Trees. Support the Arbor Day Foundation. You probably have heard of trees before. We're gonna explore what trees are, what they do, how they're useful, all that kind of stuff. So, a tree, a binary tree, is an acyclic directed graph where each node may be connected to at most two others. Oop, got a question. Boop. Okay, one more thing about linked lists, then we're going to get into trees. If you have to assign previous to null at the end of the list, does that mean you have to reassign previous to null every time you add a new item to the list? I think you mean next, but yes. So, the operation, if you're adding something to the end of a doubly linked list, I think you're talking about here. If you're adding something to the end of a doubly linked list, let's say we wanted to put something here, we would first allocate memory space, the size of one of these structures, and that allocation would return a pointer to the memory that's been set aside for it. We would instantiate all of the fields of that structure however we want them to be instantiated. So we would instantiate name, email, and pinball however we would want them to be instantiated. We would also need to instantiate the next and previous. So previous, if we were to add something to the end of the list, previous would point backwards to this guy, right? So address of this, address of the structure that was the previous end of the list will be previous for the new structure. Next will be null. And you'll need to go back into this guy and change next to not be pointing to null, but be pointing to the address of the newly created data structure, i.e. the pointer that is returned by malloc. Hopefully that answers your question. New slides aren't on Avenue yet. Oh, okay. Let me see. Sorry, guys. I finished them this morning, actually. So, yep. Content. Oh, yeah. there was one other thing, an announcement that I forgot to mention. In light of the fact that the biomed people have such a hellish week this week, I received a very polite request to move the deadline for assignment 4 back by a couple of days, because the biomed people are having a tough week. I didn't actually understand that that was like, an eighth of the class to a quarter of the class. But I agreed to the extension, so the assignment 4 is now going to be due Tuesday at midnight rather than Sunday at midnight. So, make good use of the time. Also, for those of you who may be having some difficulty with the third question, I wrote down a sort of breakdown of steps for a procedure that would work, and I posted it to Piazza. So if you haven't started question 3 on assignment 4 yet, that might help you. That might help you decompose the algorithm into its subcomponents a little better. Because the question was like, this is very large and confusing. I don't even know where to start. So hopefully that's helpful in some degree. Anyway, so trees. Let's discuss some tree nomenclature. Trees have a root node, which is R in this diagram. The root of the tree is the node to which no other node points. So you can see in this structure that all of the nodes V are pointed to by at most one other node, except for R. R is the root of the tree. And if we had a pointer that pointed to the tree, it would point to R. For every vertex V, there is exactly one path to that vertex from the root node. So in other words, the branches are not allowed to cross. You can't have this guy pointing to this guy, for instance. That's disallowed if it's a tree. There has to be always only exactly one path from any particular vertex to the root. Each node has exactly one parent, except for root, and up to 2 children. Now, this is because we're talking about binary trees here. There are actually a large number of different types of trees. Binary trees are just one type of tree. Binary trees have at most 2 children. N-ary trees have at most n children. So you could imagine like a trinary tree that has, as many as 3 children per parent node. You could imagine a 10-ary tree which has 10 children per parent node, etc., etc. Of course, the thing about binary trees is that, computers are binary systems, so it makes sense to start with binary, as a jumping off point if we're going to learn stuff. It slots itself more naturally into computer systems in general. Also, it's very useful. Even, you might think, oh, the more nodes that we have, the more, the better the data structure, but that's not actually the case. Simplicity often wins out in these types of things. So, a leaf node is any node in the tree which does not point to any other nodes. So this is a leaf node, this is a leaf node, that's a leaf, and that's a leaf. They're the end of the branches. A stem node is any node in the tree which does point to other nodes. So all of these guys are stems, and root is by definition also a stem. The depth of a tree is the number of nodes in the longest branch, i.e. the distance from the root to the furthest leaf in the nodes. So in this particular case, the depth of this tree is 3. 1, 2, 3. 3 nodes. Or 4 nodes, if you include the root. The nodes in a tree are organized into levels. So First level, second level, third level, fourth level. I'm really missing my chalkboard right now. All of the nodes of the same distance to the root node are at the same level. So, generally speaking, diagrams of trees are organized such that you proceed from, you have the highest level at the top and the lowest level at the bottom. However, this is not the only way of representing a tree. Sometimes these guys can get very, very wide at the bottom. So sometimes you'll see trees that are organized radially, so that the root node is in the middle and the... Maybe I could find that. Radial representation of binary tree. Maybe. Maybe this? Something like this? Yeah. Okay. This is a decent analogy. So, if you take a look at this, if you ignore the lines that are going like in circles and imagine that those are not edges in the graph, this would be a tree structure that does that is organized radially. You can see how if you were to make this linear, all of these nodes along here would be, you know, it would take up a lot of space. But anyway, so yeah, that's good. The width of a level is the number of nodes in that level. So in this case, the widths of each of these levels is actually precisely equal to the level number 1, 2, 3, and 4. And a set of n is greater than or equal to 0 disjoint trees is called a forest. So if you have a bunch of trees, that's a forest. Ha! Who said mathematicians have no humor? Whereas a singly linked list has only one next pointer, the binary tree has two. By convention, we call these left and right. So, if we had a very simple binary tree with just a value, just like it just contains one integer, then we would have two self-referential pointers inside of the structure. One points left, one points right. It's also possible to extend this data structure in a similar way to doubly linked lists by having a third pointer which points up to the parent node, but at this point, let's just keep it simple. One interesting property of trees is that they are a naturally inductive data structure, i.e., both nodes pointed to by left and right can be rightly considered roots of their own trees. So if you think about it, and now I'm really missing my chalkboard. If you take a look at our tree structure here, if you take a look at the left node and you sort of completely... Can I do it with a window? Maybe I can do it with a window. If you sort of obscure the other half of the tree, right, and if you also obscure R there, then this is a tree in its own right? Like, that is another tree. That's a subtree of the main tree. Same thing on the other side. If you obscure the other guys, this is a tree itself, even though, like, this looks a lot like a linked list. So we can use that just as a linked list. If you follow one node in a linked list, the rest of the list is another. This is also a linked list. It just starts here instead. The same thing works with trees. So recursive algorithms are a good choice over these types of data structures. In fact, let's talk about one. Let's talk about a tree summing algorithm. This example is to try to get you into the mind space that's necessary to think about these sorts of things recursively. Let's design an algorithm to recursively sum all of the values in a tree, assuming the tree is constructed in this manner. the sum of a tree is the sum of the left tree, the sum of the right tree, and the value of the root node. That's an interesting definition. So the sort of intuitive idea of what the sum of a tree would be is it would be the values of all of the nodes in the tree summed together. However, we can break that down. We can say it's R, we can say it's this guy, plus whatever the sum of this is, plus whatever the sum of this is. That's a recursive way of framing the algorithm, and, you know, we can construct an algorithm out along those lines. So, we need the sum of the left tree, we need the sum of the right tree, and the value of the root node. If the left tree doesn't exist, i.e. it's a null pointer, its sum is 0. So it does not contribute to the sum if it doesn't exist. If the left tree does exist, we recursively call the summing function on the left tree, considering the node pointed to by the left pointer to be the new root node in this recursive call. We then hold on to the returned value for later. We repeat those steps. It should just say repeat step 2. We repeat step 2 with the right tree. So it should say 1 and 2. If the right tree is pointing to null, then it's not contributing anything to the sum. If there is a node pointed to, consider that node to be the new root of a new tree, and then recursively call the summing function on that tree. Hold on to the value returned by that function. We add the results of step 2 and 3 to the value of the root node, and then return this value. So let's visualize it. Summing a tree. So we start off with the root node. The root node has a value of 19. The first thing that we want to do is we want to compute the sum of the left tree. So we travel via the left pointer to the first node in the left tree, which is now the root node that we're considering. However, this guy, in and of itself, we need to compute the value of the left tree, the left subtree of this node. So we follow the pointer down to this guy. This guy does not have either a left node or a right node. It is a leaf node. Both of its pointers are null. So, because left is null and right is null, they contribute 0. Those zeros are added to the value of that node, which is 81. So 81 is passed back up the tree to the node that called that node. We then perform the same operation with the right node. We travel down the right node, find the value here. Notice that the left and right nodes both are null, so those are 0 contribution. So we add zeros to the 66, pass 66 back up the tree as the return value. We can now compute the sum of this node. It's 81 plus 8 plus 66. That is not 95. Oh my goodness, that's a mistake. Oops. I think it's 195. Let me see. Oh my god. And you know what the worst part is? I didn't keep, like, intermediate. No, it's 155. What the heck is going on there? My apologies for the fact that I screwed up the math on this for some gosh darned reason. But that should say 155. Anyway, the value of the summation is passed back up the tree here. So this node is like, okay, I now have a result from the left tree. I'm now going to take the result from the right tree. So you travel down the right node. You travel that one down that one again. That one has no left or right pointers. They are both null, so the value of 67 is passed back up. That sum is computed. That's 96. That's passed back up again. This 95 is inaccurate, but we now have everything we need to compute the complete and total sum of the tree. This example overwrites node values with the results of summation, which is probably not a good idea. This is mostly for demonstration purposes. A real algorithm wouldn't overwrite node contents like this, but, you know, it's for the purposes of demonstration. Yeah. Any questions about that? So, I should actually wait. So, this algorithm is presenting an example of what's called depth-first search. So, because this algorithm goes as far as it can down a particular branch and then backtracks, that's what's known as a depth-first algorithm. Searching a tree can go very differently depending on how you approach it. Generally speaking, for operations over trees, you've got depth-first algorithms and breadth-first algorithms. In particular, you hear a lot about depth-first search and breadth-first search because, of course, searching algorithms are a, common and well-understood area of algorithm application. So, in depth-first search, you select a branch and follow it down until you find a leaf node. Once you have found a leaf node, if you haven't found the item that you're searching for, you backtrack to the most recent stem node that has a branch that you haven't tried yet, and then you try that branch. And, in that mechanism, you can traverse the entire tree. Once there are no branches left that you haven't tried, then the algorithm is considered to have completely searched the tree. It is very important to note that this algorithm only works if there are no cross branches within the tree. A cross branch within the tree will effectively have the tree researching itself, duplicating searches that it's already performed over itself, let's say. This type of algorithm is suitable for exploration of decision branches in game AIs. So, if you consider a chess AI, right? It doesn't have to find the overall best move. All it has to do is all it has to do is go with the first solution, the first set of moves that it comes up with that result in victory, right? You don't need to know the space of all possible victories because it's way too wide in a game like chess, right? The number, that's the number of permutations of different moves you can make in chess is extremely large. So because a depth-first search doesn't have to traverse the entire tree, it just has to run until it finds a suitable result, this is the preferable type of search for that type of application. If we consider breadth-first search, what happens is it goes by level in the tree. So it searches all of the nodes in one level of a tree before moving on to the next. This requires more traversal and bookkeeping than depth-first search, but it also finds minimum branch depth much, much faster than depth-first search. For depth-first search, in order to find the minimum branch depth, you basically have to traverse the entire tree. Whereas with breadth-first search, you only have to traverse the tree up to the point where you find the first leaf node, and that's whatever level you're at, that's the minimum depth. So, as with many things, which algorithm you use is largely dependent on which application you're applying it to. Depth-first search and breadth-first search are popular topics among people who think that computer algorithms have applications to human behavior. You can look that guy up if you like. So, we can finish this slide set today. Let's do it. Binary search trees. Both depth-first search and breadth-first first search assume nothing about the structure of the data contained in the tree, aside from the fact that it is a tree. If we give trees certain mathematical properties, we can write algorithms that vastly improve general case runtimes. Similarly to how if you assume a list, if you assume that an array is sorted, you can perform binary search over it, which greatly increases the amount of, it greatly decreases the runtime required to find anything. In the same way, if a binary tree has the binary search tree property, it allows us to search the tree extremely quickly without having to iterate over every single node in the tree, as you would need to if you were using depth or breadth first search. So this is the binary tree property. If a node has a left child node, the value of that node is less than or equal to the value of the parent node, and if a node has a right child node, the value of that node is greater than the parent node. So if the value of a node is x, then the left one is less than or equal to x, and the right one is greater than x. Depending on who writes the definition, duplicate elements are sometimes disallowed. It really largely depends on whose formulation of a binary search tree you go with. Some of them allow duplicate elements, some of them don't allow duplicate elements. This particular formulation is one in which allows duplicate elements and shunts those duplicate elements down the left side of the tree. So, pros and cons. So why would we want to use a binary search tree? The best case scenario runtime for search, insertion, and deletion operations is big O of D, where D is the depth of the tree, the number of levels in the tree. In the best case scenario, the depth of the tree is log base 2 of n, where n is the number of nodes. You can imagine an optimally configured... let's see. So this guy right here, this is an optimally configured tree, right? Because the number of nodes is the number of nodes in each level is 2 to the power of that level, right? So in order to, because we can make decisions on which side of the tree we need to traverse based on the value that's contained in that node, right? If we're looking for some, it's the same, it's very similar to the binary search algorithm. Like, say, if we're looking for 7 and this is a 3, we know we need to look in the bigger side of the tree, and we can continue making informed decisions about which side of the tree to traverse all the way until we reach the lowest level. So, in the best case scenario, you have a tree that looks like this, where you have the maximum number of nodes in each level. That makes it easiest. In the worst case scenario, you have something that looks like a linked list. Like technically speaking, a linked list can be considered a type of tree, although it's kind of like a unary tree, like but you know, a linked list is a valid binary tree. Like if you in the set of graphs that are described by the binary tree description, linked lists can be included in there. So, your worst case scenario for searching a binary search tree is that everything is in line. So the depth of the tree is equal to the number of elements in the tree. In that case, you have to check every single one of them, which means that your worst case runtime is the number of elements in the tree. And of course, your average case runtime will be somewhere in between. Yes. The search tree property, so one of the cons is the search tree property must be maintained, which requires some extra bookkeeping, but again, the bookkeeping is usually worth it. To address the drawbacks of unbalanced trees, that's what you would consider that very linear, like one branch tree. Binary search trees in practice often use balancing algorithms, such as red-black trees, or the Adelson, Velsky, and Landis, or AVL tree. You know, there are ways that you can, like, shift the balance in trees such that, they maintain some degree of balance. But yeah, so that's binary search trees, pros and cons. Question. As the programmer, would you have to know every single node in the tree you're making? Like for the chess example, it seems kind of impossible to know every single move in chess and make them each a separate node manually. Yeah, so the problem that there begins to be a gray area between, I'm gonna put the last slide comic up while I talk about this. There's a bit of a gray area between, like a decision-making algorithm and a tree-like structure. Like if you think about it, when you're writing an if and an else, right, that can be constructed as two branches in a structure, right? And like your decision structure can be represented as a tree. Whether or not each one of those decisions has some corresponding element in memory, which is modified or something like that, it's sort of, it's not quite a memory application. It's more of an instruction application. But certainly, it would also be possible to subcategorize things in a tree, like, in a chess algorithm, you could choose to, like, you could have as possibilities, all of the possible, like, I want to move my knight. These are all of the possible moves a knight can make. I want to move my queen. These are all the possible moves a queen can make. Generally speaking, when you're trying to design an algorithm like that, the thing that you are focused on is trying to restrict the search space. You want to restrict the like, obviously the search space is enormous, right? And the more you can restrict the search space, the faster your algorithm is going to run. So the trick with restricting the search space is you want to make assumptions about the nature of the game or the algorithm that exclude possibilities, and the excluded possibilities do not contain too many winning scenarios, right? You want to maintain at least one winning scenario within the search space that you are maintaining, right? But you can exclude large amounts of other search space. Like, for example, as I understand it, with chess algorithms, the way that a lot of them work is that it doesn't look like the number of moves ahead that you look. That's what really adds to the search space complexity, right? So you could have a chess strategy that like, for example, only looks 3 moves ahead, but within those 3 moves will exclude any branch that results in like loss of points. If you know the analogy, like the chess piece points analogy, where pawns are worth 1 point, knights and bishops are worth 3, rooks are worth 5, the queen is worth 9, and the king is worth the game. Like, if you can write an algorithm so that it's so that it restricts the search space by making sure that if one of its pieces is captured, it can immediately capture something else that's worth equal or more points. And that's the kind of thing that a human does when they're playing chess as well. Generally speaking, you don't want to lose too many pieces. But the losing pieces heuristic is not, like, it's a heuristic, right? It's not
it's not a perfect way of simplifying the game of chess because, you know, you can lose all kinds of pieces, but as long as you maintain at least a couple, it is possible to force checkmate, right? You don't necessarily need to be optimizing for keeping the maximum number of pieces as long as possible to be winning the chess game. But that's the type of heuristic that you would use, right? So yeah, going back to memory, very often in these algorithms, like, we're talking about them in more general terms, and they're applicable to more things than just memory management, right? Like, you know, once you start getting into things like, you know, flow networks and the traveling salesman problem and things like that, it sort of becomes a bit ambiguous whether you're dealing with, you know, hard mathematical data or, you know, decisions and decision costs and that sort of thing. The mathematical abstraction applies equally to both. Linked lists are a little more well-grounded in memory management, but trees have a much greater degree of applicability to many more situations. But yeah, certainly you can use binary search trees and things like them to for like direct memory management applications. I believe I read somewhere that some operating systems use binary search trees to manage the memory allocation operation, like malloc. The way that on some computers, the way that malloc actually finds the space in memory for you to be able to have is that it organizes the memory into, it organizes a representation of the memory as a binary search tree and traverses that to find, you know, contiguous memory elements that are sufficiently large to be able to allocate to you. I'm not sure, like, I haven't, if I had worked that out into a complete slide, I would, you know, have a better idea of how that worked and I would be able to tell you. But hopefully that answers your question. Hopefully that answers your question. I should probably stop talking as you guys have classes to get to. But, yeah. Any other questions? Okay. Question: why am I wearing these headphones? Comfort. I don't know. Without them, my head feels naked. I don't know. I know normally, you know, I was using the microphone on the headset, but apparently it's inferior to the one that's in my laptop, so I've been using the one in my laptop, but yeah. Also, like, I occasionally listen here, and I don't know, it just feels better if it's on my head. But yeah, it's, I don't know. Aesthetic considerations? Anyway. Take her easy, folks. I'll see you guys on Thursday. Thursday, we're going to talk about Topic 8. Topic 8 is going to be, let me show you quickly slides. Topic 8, I'll show you the title. We're going to talk about the C preprocessor and miscellaneous errata. This is actually going to be the last slide set on C programming that we have in this course. So, huzzah! Take her easy. And if you're writing that anatomy midterm, remember, skull, clavicle, elbow. Have a good day.